Hi, this is the next video for the Year 1 Pure, and we're looking towards 7C. Now, oh no, we're not, sorry, 7D. Proof is a difficult topic, it's a strange topic. There's no one technique. It sort of builds on everything that we do in all other areas. So sometimes it's just work through some algebra and it's straightforward. Occasionally it's difficult to know what to do. And the only way to develop these thinking skills is to practice lots of questions. So I'll go through the examples, but there's not a lot more maths to learn here. It's just some demonstrations of proofs that you might be asked. So 7D and 7E are both interesting, although difficult to know quite how to develop the skills other than just practicing lots of questions. Okay, so example 8. Well, it's just multiplying out triple brackets, and I'm not going to show you how to do that. But it says, prove that 3x add 2, blah, 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 is identical to 3x cubed. And I suppose the point of this example is you start with a line and you work through logically and reach the conclusion that you need. But you know how to multiply out triple brackets, so I'm not going to bother showing you how to do that. Example 9 is an interesting one. Essentially, it's saying, prove the factor theorem. Prove that if x minus p is a factor of f of x, then f of p equals 0. Now, we take that as read when we use it for the factor theorem, but although we've seen it happen for a few examples, we haven't necessarily proved it. So what we're doing here is we're going to assume that it is true. If x minus p is a factor of f of x, then we can write f of x is x minus p multiplied by some other function, g of x, where g of x is a polynomial. So I'm saying that if f of x is cubic, for example, then my cubic must be equal to my linear expression times by a polynomial, which in that case would be quadratic. But of course, it could happen for any order. So if that's true, then that's true. And if that's true, f of p is p minus p times g of p. I don't know what g of p is, but crucially, it's 0 times g of p, which equals 0. And mathematical notation, a little square says, there you go, proved. You could do a tick, you could write QED, you could write as required. I quite like the little square, so I stick with the little square. No new maths there, but just showing you an example of a proof. Example 10, again, no new maths. I need to prove that these points are the vertices of a right-angled triangle. So prove that A, B, C are the vertices of right-angled triangle. Now, I'm going to prove that they're the vertices of a triangle, and then prove that they're the vertices of a right-angled triangle. So let's look at the gradient AB, difference in y over difference in x. Let's look at the gradient of BC. Difference in y over difference in x. or because they're different gradients, they can't be on the same line, but we'll also look at the gradient of AC, difference in y over difference in x. So there can't be, gradients are all different, so A, B, C cannot be collinear on the same line. So that means they must be a triangle. Now, a quick sketch, A, 1, 1, B, 3, 3, and C, 4, 2. That's not necessarily to scale. The gradient of AB is 1. Well, the gradient of BC is minus 1. And that's minus 1 over 1. So the gradient of BC equals minus 1 over the gradient of AB. Therefore, BC and AB are perpendicular. So I've got a triangle and I've got a right angle. ABC is a right angled triangle. So I've proved that there must be a triangle. If they're not on the same line, there must be a triangle. I've proved that there's a right angle because two of the gradients are negative reciprocals of each other. Therefore, I've got a right angled triangle. Example 11. Now this is an interesting one. On the face of it, it looks like stuff that we've seen before. Let's just write it out. If given that, prove that k is greater than or equal to 0 and less than 8/9. And we're saying that this has no real roots. Okay, so no real roots means that b squared minus 4ac is equal to 0. No, it doesn't. It means that it's less than 0, sorry. So 3k squared minus 4 times k times 2 is less than 0. None of this is new. You've seen this a billion times before. Take out my k, 9k minus 8. Sketch the quadratic, always with a quadratic inequality. So k must be less than 8/9 and greater than 0. But I need to prove that it's greater or equal to 0. Now remember what that means. These values of k means that there are no solutions to this equation. So I've covered nearly all of those. I'm going to try k being 0 separately. And what I want is, if k is 0, then there's no solution. That's what I want, because then I can add on my equals bit. So if k equals 0, kx squared plus 3kx plus 2 equals 0 plus 0 plus 2. And since 2 is not equal to 0, there's no solution to the original equation. Or k equals 0 is not a solution to the original equation. So not only does k have to be greater than 0, for there to be no real roots, not only can k be greater than 0, it can be equal to 0. Therefore, k can be equal to or greater than 0 and less than 8/9. So that's an interesting question, and that is a subtle difference to that which we're used to. Okay, give 7D a shot. Let me know if you need anything. I'll see you next time.